So today we're going to talk about adiabatic reversible expansion. And what we're going to start with when we're talking about this is we're going to start with our container. Let's just use a cube for now. And we're going to use a positive direction, which is going to be our z. It's going to be our z. And this right here is going to be our derivative of z. Here, we're going to have our actual z value. Up top, we're going to have our area. And then this distance right here, this is going to be the derivative of our z plus our z, dz plus z. So this is what's going to help us find the weight of, or the expansion of our water, and or whatever liquid it may be. And we're going to use Newton's equation, force equals mass times acceleration, to help us find this as well. We're also going to have pressures from the bottom and the top that are going to be pushing up and down on our little sample area here. So we're going to have this pressure, which is going to be the pressure at the point Z. So pressure at the point Z times our area. And then up here, going down, we're going to have the pressure at dz plus z times that same area. It's right here. And so those pressures are going to be both pushing up and down on it, as well as the force of gravity, G, that we already have. And this specifically is just our sample size. So our main, everything that's encased in here, here's our cube. The fluid that's encased in here, this is also fluid, is going to have a constant velocity. So the velocity is going to be constant. And that makes our acceleration 0 for the bigger area, not just the sample. So now what we need to do is sum up our forces. So see, the sum of forces 0, and so the forces are equal to, in the positive, if we have the positive going up, we say pz times a minus our p dz minus z times a minus our mass times our gravity. It's the mass of it, and then the gravity is going to be, that's why we're subtracting. That's going to be equal to 0. And the way we can solve this is first by putting mg over here, over on the other side. But we can also replace our mass to try to replace some of these values. So our mass is going to be equal to the density times our volume. And to figure out our volume, we just try to figure out the volume of a cube, which is the area of the base times the height. So our volume is going to be equal to our area times our dz value, which is our height. So we can switch this over to this side, but also replace mass, or replace mass with our density times our volume. So we can say, we can also factor out an a here, just to start. So let's just say negative a is equal to pz we say it's going to be, we're going to switch these. So it's going to be P dz minus z minus our pz equal to our mg. But our mg is going to turn into our density times our volume, which is A dz, and then times the gravity. And what we can do now is we can also factor out our area. Factor it out. It'd be equal to negative P dz minus z minus pz. So it'd be equal to our density times dz times our g. This technically is our dz because it's the change in our z value. So this is going to be, this can turn into, if we divide this side by our dz, we can have, or this is going to be our difference in our pressure. So, or this is going to be the change in pressure. So we can have, this is going to turn into our dp over dz, and we can move the negative over to this side, and it's just going to be equal to our density times our negative density times our gravity. As we move the negative over to this side, move the dz over here, and change this into just dp. And now we need to incorporate our ideal gas law. And we remember that is PV equals nRT. And we need to find how to fit this into our density. And the way we're going to do that is we're going to say that we're going to change this up a bit and say that our n over v is equal to, it's going to be equal to P over RT. But we also have to account for that NV that we don't really want. And so we're going to say that our density is equal to mass over volume. We need to incorporate our moles, so it's going to be moles times our molecular weight, volume, and this is eventually going to turn into our density being equal to PM over our RT. This is our density, which we can put back into this equation. So we're going to say dP over dz is equal to the negative PM over RT times RG that we still have. And this equation right here, this is what's going to help us out in part 3, where this is going to come back in part 3. This is what we need to carry over. So to start part 2, what we need to realize is that we're going to be working with thermodynamics, but we also need to incorporate our ideal gas law to help incorporate that first equation that we got. And what we're going to start with is the first equation of the first law of thermodynamics, which is going to be the change in our external pressure is going to be equal to the change in our heat minus the pressure times the change in volume. And what we're going to look into is a pocket of air that is changing. So a pocket of air starts here. Let's just call this P1. And as it rises, the volume is going to increase. And that's going to be called P2. And once this pocket of air, once it rises, the volume is going to become greater. And we need to worry about our external pressures forcing down on the pocket of air. And so that is just going to be, just our pressure is going to be equal to our external pressure. And this is going to give us our equations for P1 and P2. So P1 external pressure times the external pressure, and P2 times the external pressure. And what we can do is get rid of this change in heat, because that's just going to be zero for our purposes. So this is going to give us the equation, the change in the internal energy is going to be equal to that negative external pressure times our change in volume. And then incorporating our ideal gas law, we need to replace this pressure, but we also need to replace our internal energy. So our internal energy, du, is going to be equal to the specific heat, CV, times our change in temperature. And that can replace our du here. And then our pressure we can replace with the ideal gas law. Pressure is going to be equal to RT over V. And so replacing this in the equation, we get our specific heat times our change in temperature equals negative RT over V times our change in V. And this, to solve this, we need to solve it like a differential equation and get T over to this side. So that's going to be CV, or specific heat, times dt over T equal to, or negative R times our dV over V. And what we can do now is integrate. And we're integrating from here, we're integrating from the temperature 1, so the temperature at this point, and then to the temperature at this point. So our first starting point to our second point. So it's going to be the temperature here to the temperature. That's what we're taking the integral of. T2, and then the same thing, volume here, and then volume at our second location. Volume 1, volume 2. And so now we can just integrate. This is going to turn into, these are both going to turn into natural logs. So we're going to have the specific heat of natural log T1, T2. It's going to be equal to negative R times natural log of V from V1 to V2. And so we can just make that, integrate this, T2 over T1, natural log, equals negative R, is a natural log V2 over V1. And we can turn this, we want to get rid of these natural logs. So we are going to put our V1 and V2 into, or our specific heat and our R into a exponent. We're going to put it into an exponent. And the way we're going to do that is we're going to say, let's just put it over here. Our T2 over T1 is going to be equal to our V2 over V1 of our specific heat divided by our negative R. Actually, this needs to be our negative R over our specific heat, not our specific heat over our R. And so now we can once again incorporate our ideal gas law. So we are going to have, our V is going to be equal to our RT over P, I believe. And so now we can replace this volume in this equation and say T2 over T1 is equal to our temperature 2 times our first pressure over our second pressure times our first temperature. This is going to be equal to our negative R over CV, specific heat. But we have T2 over T1 over here, but we also have T2 over T1 over here. So we can move it over to this side and say T2 over T1 to the 1 plus R over CV is equal to P1 over P2 to the same negative over CV. Now now we're here, so to get rid of this 1 plus R over CV, we can just multiply by the reciprocal, but it's going to equal CV plus R all over our CV. That's just relating this one, multiplying CV, or just combining the fraction. So we're going to have our equation T2 over T1 to the 1 plus, or I guess it is actually, to the CV plus R over CV. And then that is going to be to the CV over CV plus R. So that's going to cancel that out. And then we're also going to multiply it by the other side, because once you do to one side, you have to do the other side. So you say P1 over P2 is equal to negative R over CV, and this times this, our CV plus R all over our CV again. Oh no, whoops. It should just be CV over CV plus R, because we're multiplying by that on this side, and we're multiplying by that on this side as well. And that will leave us with just our T2 over T1, because these cancel, the reciprocals as they cancel, equals our P1 over P2, oops, P1 over P2 to the negative R over CV plus R. And this is the equation, this is the second equation that we're going to use. We're going to combine the first equation and the second equation in part 3. And these are going to help us get our final answer for the reverse adiabatic expansion. So for part 3, what we're going to do is we're going to combine these two equations and use the equations to solve for our pressure versus altitude and our temperature versus altitude. So what we need to do is start by combining these equations, and I want to make it a little easier. So I'm going to make this exponent equal to just a variable, and we're going to call that let's call that epsilon. It's equal to negative R over specific heat plus R. Okay, so that's our epsilon. So now we're going to combine these, and we're going to say our negative P, actually, let's do this somewhere else. We're going to say our dP over dz is going to be equal to negative P M, and this is going to be P1, PMG all over our T1. We're going to multiply by our second equation, P1 over P to the epsilon. Actually, this top one is going to be P, and this bottom one is going to be P. And what we're going to do now is simplify our P's and say that dP over dz is equal to our negative mg and then P to the 1 plus our epsilon, combining these P's, and then we're just going to have our R, T1, and P, yes, and our P1 down on the bottom. And now we can move everything to different sides. So we're going to have our dP times, we're going to move our dz over here. We're going to move this P1 plus epsilon over here. So it'll be reciprocal. And so we'll say times P E minus 1 is equal to our negative mg over R T1 P1 times dz. Looks like I forgot to multiply through my epsilon here, and then also my negative sign here. So this epsilon is going to be added here, and this is going to be, instead of E minus 1, this is supposed to be negative 1 minus our epsilon, I believe. And then our epsilon should also be added here. Yes. And now we can take the integral. So we're going to take the integral of our of our dp times p negative 1 minus epsilon equal to negative mg r t1 p1 epsilon integral of dz. Now we have to remember that we're dealing with going from a pressure here to a pressure here. So we have this smaller pressure, or this smaller pocket of air to this bigger pocket of air up here. And for the smaller one, we're going to use values P1, P1 and our value Z1. And then up here, this is our final value, so we're going to use P, F, and Z, F. And so now we can integrate. And so we're going to say our integration is going to be negative 1 over epsilon to P times P to the negative epsilon. And this is going to be equal to our negative mg over rt. And then I want to put this P1 to the epsilon, make it a little easier, put it in the numerator and say P1 to the negative epsilon. It's going to help us because we already have that here and that here. And the integral of dz is just going to be z evaluated from z1 to zf. And this p is also going to be evaluated. Oops. This is also going to be evaluated from P1 to PF. We now need to use this to try to get our PF, our final pressure. And so we're going to say, we're going to utilize some of this space up here and go up and say, we should multiply this over here, get rid of this negative, and get rid of this epsilon. So we're going to say P F to the negative epsilon to the negative epsilon minus P1 to the negative epsilon is going to be equal to the P1 of our negative epsilon times mg times our epsilon that we multiplied from over here, or 1/3 epsilon, or 1 over epsilon, sorry, or we multiplied negative epsilon over here. So that's why this is now positive. All over RT, and this is going to be multiplied by Z final minus our Z initial. And then this can be simplified into pressure final to the negative epsilon equaling, these can be factored out, so pressure initial to the negative epsilon times mg epsilon over RT1 times, once again, RZF minus Z initial. And then to get rid of this negative epsilon, what we're going to do is multiply by -1 over epsilon to get rid of that. So we're gonna come down here and we're gonna say just PF, because we're multiplying by -1 over epsilon, equals P initial times mg epsilon over RT1 times CF minus Z initial, and all of this is going to be to the -1 over epsilon, because that's what we're multiplying by. Yes. Wait. I forgot to factor this out. Okay. So what we need to do is when we factor out here, we need to add a 1 plus, because when you factor out both of these, 1 plus, because you're going to be adding this one over to this side as you do this equation. So that one needs to be there, and then all we need to do is just add a plus 1 plus here. And that should keep us with where we need to be going. Because this was added to this side and they were factored out. And so that's what the 1 plus mg epsilon over RT1 is for. But all of this is being multiplied by -1 to the epsilon. Our final equation that relates our pressure and our altitude. We just need to replace this epsilon and this R. So we're going to say our final pressure is going to be equal to our initial pressure times, because we're dealing with a negative, we're going to say 1 minus mg, oh wait, no, not epsilon, mg over, R is just going to be CV plus R and plus T1. So we're just replacing our epsilons, and that's good for that one. And we're going to stay with our ZF minus ZI. And because we have this -1 over E, our epsilon, which is up here, is going to turn into positive, and then we're going to flip over the fraction. So we're going to say CV plus R over R. And this, this is our final equation that relates our pressure to our altitude, because our pressure final is dependent on the Z final and the Z initial that we started right at the start of this, which is the corresponding value going up and down, and the positive Z direction. And to find the relationship for temperature and altitude, we can use the equation we already have. So all we're going to do is use the equation we've just gotten, but using our epsilon, and using this equation that we have right here, that we found for our in part 2 for our second equation. So that equation for our temperature final is going to be our temperature initial times our initial pressure over our final pressure, raised to, you guessed it, the epsilon power. So we have this equation, and knowing that our final pressure is equal to all of this, we can sub back in under here. But it's going to be a lot easier because we can cancel out these epsilons, and we can also cancel out, or we can replace this epsilon here. And this will also cancel. So our PIs will cancel, and so we are going to be left with something like the final temperature is equal to the initial temperature of PIs. This will cancel with this. It's just going to be a very similar thing. So it's going to be, yeah. It's going to be 1. Oh, oops. It's supposed to be 1. It's just going to be 1 plus mg over our r, which is going to cancel after we put in our epsilon. It's going to do the same thing that this did, so it's just going to be CV plus R times the initial temperature. Again, this times ZF minus Z initial. Close both those parentheses, and this will be our final equation for. This will be our final equation that helps us find our temperature final. This equation relates the temperature in the altitude, and this equation relates the pressure in the altitude. And that will finish our part.